Hello, everybody. This will be the first video I will make on an introduction to abstract algebra course. This is going to be, I think, very exciting. I think abstract algebra is very beautiful, is very interesting, and it's definitely a starting point for a lot of really important mathematics. So it's very important that not only you're able to, do the basic abstract algebra problems, but that you're also able to understand intuitively what is going on. So I'm going to try to put a little bit of emphasis on that. As far as prerequisites, the only thing that you need is a little bit of linear algebra. It's actually not that important. We're not going to use any of the really advanced linear algebra stuff, at least not until the later parts of the course. But more than anything, I think having a little bit of mathematical maturity is going to help out a lot. But I'm going to try to ease into some of these topics. I'm going to try to be, a little bit cautious with the way I present these topics. I want it to be accessible and easy to understand, okay? And the book we're going to use is Herstein's Topics in Algebra. Hopefully this book will help you a lot. It has helped me a lot to understand a lot of these topics on an intuitive level. So one of the great things about abstract algebra is that it is almost entirely self-contained. So except for some linear algebra stuff and maybe some number theory, some very elementary number theory things, we should be able to, really focus on the important parts, okay? On really trying to understand what is going on. So the first idea that we're going to go through this course is the notion of a group. So what is a group? What is a group? Now, the classical notion of a group is given by very famous axioms. There has to be a product, there has to be an identity. The product, well, it needs to be closed, obviously, and every element needs to have an inverse. I don't want to lose a lot of time on that. Hopefully, most of you are already familiar with some of these ideas. What I think is very useful is the following diagram to understand what it means for a group, for the operation to be associative. So the way I would represent this is by, we would need to put like this, maybe this, and yeah, so something like this. And we want this diagram to be commutative in order for the product to be associative. I think, yeah. Just think about this for a little bit. It should help you understand intuitively what is going on with the associativity of the product. So let's talk about some examples of groups. A very natural example is the integers under addition, a very common one of the most important examples of a group. Another very common example is, say, the matrices with complex entries, invertible matrices, under multiplication. An even more natural example, in my opinion, is, fix a natural number n. We can talk about the nth homology group of a topological space, whether we're talking about simplicial or singular or cellular. These are all groups, and these motivate a lot of mathematics, especially like a lot of algebra. Homological algebra is a great example of a field of an algebraic object that actually started in topology and that ended up being understood in algebra. Another very important example, and hopefully this will single-handedly motivate you to learn group theory, is Lie groups. Lie groups are groups. So moving on. A very important notion of groups are, we have our category, we have our objects that are groups. Let's use G1, G2. And we want to understand the arrows between the objects. We want to understand the morphisms between groups. So phi is a group morphism, sometimes called homomorphism. In fact, Herstein uses homomorphism. I prefer group morphism. It's a group homomorphism if it preserves group structure. Again, very natural. Okay, very natural. So what does it mean for a group morphism to be an isomorphism? Well, I'm going to use a very standard notation used by Bernstein. We'll say that a morphism is an isomorphism if it's a group morphism that is injected. Some people call these monomorphisms. I really like Bernstein's notation, and to refer to this as isomorphisms. We'll say that two groups, G1 and G2, are isomorphic if there exists an isomorphism in the categorical sense. That means that phi is an isomorphism that is surjective, or alternatively, it's a group morphism that is bijective. Okay, so it's important that you understand this. Watch out, because in order for two groups to be isomorphic, we need to have a categorical isomorphism. We need to have a categorical isomorphism, which is not the same as an isomorphism, because an isomorphism need not be surjective. It will always be injective, but not always bijective, because it might not be surjective. Okay, so hopefully this idea is very natural. Again, we want to go back and forwards with our arrows. So we want our isomorphisms to be invertible, which again, they may not be, because they might be injective but not surjective, and they might not be isomorphisms categorically speaking, but they will always be morphisms categorically speaking, but not always isomorphisms. Okay. Hertzane, I think absolutely it's the nail in the coffin with this notion of an isomorphism. What else can I say? Okay, moving on to the next topic, one of the most important topic of groups theory, it's group actions. So we have a set X. X doesn't have to be a group, X can be anything. We want a group to act on it. So we want to have X, elements of X, and we want to multiply them. And hopefully like this drawing helps you a lot. This drawing helped me so much to understand what a group action is, right? Yeah, so if you ever get a little bit confused about group theory, look at this picture. This picture will tell you everything you need to understand about groups. Okay, great. So one natural consequence, again, this is very combinatorial in nature, is this formula. This is the center. The center is very closely related to the abelianizer of a group, just so that maybe you can understand it a little bit more. And we have the indices of a group, of a subgroup, the index of a subgroup on G. Speaking of which, there's a very important action, which is making G act on a subgroup. A subgroup, I didn't say this, it's very natural, but a subgroup is a group inside of G, right? This is it's a group that is a subset of G that also has group structure. So this action is very natural. Just replace an X with an H and it just works fine, right? It's very natural. And this leads to Lagrange, which you can read more in the book, but it says that the order of H divides the order of G. The order is a number of elements. So the elements of a subgroup will always divide the number of elements of a group, which is a fabulous theorem. And I think it's very intuitive, again, if you just understand this a little bit, this picture. Okay. So this idea of Lagrange and this action will naturally lead us into talking about quotients. Okay, so what is a quotient? So the quotient is the most important idea of this course. Like I would go as far as to say, if you don't understand what a quotient is, then you should not pass this class. This is the most important concept in abstract algebra. So a quotient is a good way to understand it is, if we have a morphism, we want to factor this morphism with some quotient that verifies the universal property, right? So if we want for the, the morphism to verify the basic properties that we want to, essentially what this is saying is if a morphism verifies the properties that we want, right, that contains, its kernel contains the set, the subgroup that we're interested in, then there will be another morphism so that it verifies the property that we want to, that is, that makes this diagonal commute. So if the basic conditions work out, we will have our basic result, that is that this can be factored, and this will, have to put a projection. Again, very natural, hopefully. If you get confused about this, this is another very important, this is the universal property, the universal quotient rule. And you can prove, it's very easy, you can prove that this object is unique in the category, meaning that if another object exists, there is a surjective isomorphism, or equivalently a categorical isomorphism between the object that verifies this property and this object here. Okay, again, hopefully pretty natural. Okay, so another important action, as you see, actions are very important, is the action of a group onto the silo of the p silos of a group. And the action is very natural. The product will just be the conjugation, right? So in order to understand what a p silo group is, we need to understand what a p group is. And a p group is it's a group of order p, p to the n. So 2, order 3, 5, 25, 49, I don't know, 7, 5. Did I say 5? I think I said 5 already. 11, not 10, because 10 is 2 times 5, which is not a power of p. So that's not a p group. Now a silo subgroup is a subgroup of G that it has the biggest power of P as its order. So a silo will have the order of a silo. We'll have a P raised to the maximum n such that P to the n divides the order of G. I think this is, this is too collapsed. I need to explain this a little bit better. It means that it's P to the, how can I read this? It's the max n such that, if we describe the order of G to P to the n times Q, then this n has to be the maximum. Okay, so far so good. Okay. So this should pretty much cover everything about groups that you need to know. Oh my God, I almost forgot. Oh my God, sorry. This is so important. We'll say that G of X is transitive, an action is transitive if G acts transitively on the elements of X. Yeah, this is so important. I can't believe I almost forgot. Yeah. So with this, and again, this picture, you should hopefully be able to understand chapters 1, 2, 3, 4, and 5 of the book. If you struggle a little bit, you can ask me. I'll try to help you out on the comments below. But this should give you like a very intuitive understanding of what is going on group theory. Okay. Yeah. Yeah, we have a little bit of time left. I took a little bit too long here. I really wanted to make sure that all of these topics got the proper amount of time. So I'm gonna start off with rings. I'm gonna do a little bit. I don't have time to do everything I want to do today, but a ring, in order to understand rings, we need to understand ideals. Ideals are like the things that we care about rings, right? So when we talk about rings, we care about, okay, what are its ideals? That's what's really important. And in order to understand what an ideal is a special case of a module. So it's a special case of a module. What is a module? Well, a module is a vector space but its scalars form a ring. So they might not form a field, but they will form a ring. So again, in order to understand rings, we want to understand its ideals. Ideals are modules. And modules are just vector spaces, but over a ring instead of a field. So hopefully this gives you an intuitive understanding of what is a ring and what is an ideal. Okay, we'll still talk a little bit about rings on the next class though, so don't worry if you struggle a little bit on this part.